Welcome to this explainer. Today, we are going to unpack the hidden, microscopic quantum physics that literally power one of the most ubiquitous technologies in our modern world. We're demystifying the laser. We see them absolutely everywhere, from big sci-fi movies right down to our local grocery store checkouts. But the actual science happening at the atomic level inside these devices is absolutely mind-blowing. So let's dive right into this and uncover the quantum rules that make it all possible.
To really understand this technology, we're taking an inside-out approach. Here is our roadmap for today. Lasers in our daily lives, anatomy of an acronym, ordinary versus laser light, the secret of stimulated emission, and finally the 4 pillars of laser light. Let's get started.
Section 1. Lasers in our daily lives. We rely on this technology constantly, usually without even batting an eye.
Just think about the sheer variety of applications here. It's staggering. We're talking about scanning our groceries with barcode scanners, printing documents, laser cutting, all the way to performing incredibly delicate, life-saving eye surgeries. They even form the very backbone of the internet through fiber optic cables, and they're used for super precise distance measurements and free space communication. These highly focused beams of light are absolutely everywhere in our modern infrastructure. But to understand how one single technology can do all of these vastly different things, we really need to understand what it actually is.
Which brings us to Section 2, Anatomy of an Acronym. We all know the word laser, but to uncover how it works, we first need to realize it isn't a word at all.
It's actually an acronym: Light Amplification by Stimulated Emission of Radiation. And the absolute crucial mystery we are going to solve today lies directly in that middle phrase, stimulated emission. That right there is the magic ingredient.
But before we get deep into the physics, let's look at the timeline. The whole concept actually traces back to a theoretical prediction by none other than Albert Einstein. His prediction kind of just lay dormant for decades, until it finally saw its first practical use around 1954. Then, fast forward in 1960, a scientist named T.H. Maiman developed the very first practical laser device using a synthetic ruby crystal. This first ruby laser emitted a brilliant, highly focused red light with a wavelength of exactly 694.3 nanometers. It was a massive, game-changing breakthrough.
Section 3. Ordinary versus laser light. So what actually made Maiman's ruby laser so profoundly different from, say, a regular desk lamp?
Well, ordinary light is created through something called spontaneous emission. This is where an atom's electrons naturally and completely randomly fall from an excited high-energy state down to a lower energy level. When they make that drop, they release a photon of light unprompted. The absolute key word to remember here is spontaneous.
In the physics world, this is known as the A21 process. And because these photons fire off in completely random directions with absolutely zero phase relationship to one another, the resulting light is, well, it's messy, it's ordinary, it spreads out everywhere, and it's highly incoherent. You can think of it like a noisy, disorganized crowd of people all just talking over each other at different volumes and walking in different directions. That is exactly what's happening with the light illuminating your living room right now.
Now we get to Section 4, the secret of stimulated emission. This is the precise mechanism that transforms that chaotic crowd of light into a perfect, uniform beam. Unlike spontaneous emission, where atoms just drop their energy randomly, stimulated emission is a highly controlled interaction. During the brief window an atom is sitting there in an excited state, an incoming photon, one with the exact right amount of energy, comes along and literally forces that excited atom to release its energy early. The result? The atom drops its energy and releases a twin photon.
The crucial point here is summarized perfectly by this quote from our source material. The direction of propagation, phase, and energy of the emitted photon is exactly same as that of incident photon. This is just incredible stuff. Instead of random light, you now have 2 photons moving in perfect lockstep. This perfectly coordinated chain reaction creates an enhanced beam of completely synchronized light. We've essentially taken our noisy, disorganized crowd and turned them into a perfectly rehearsed choir, all singing the exact same note at the exact same volume, right in the exact same direction. Mathematically speaking, this unbelievably precise synchronization process is called the B21 transition, and the math dictates that the probability of this stimulated emission happening actually scales up directly with the energy density introduced into the active medium. So simply put, if you pump more targeted energy into the system, you dramatically increase the chances of forcing these atoms to synchronize their light output.
But here's the catch. It's the golden rule of making all this quantum physics work in a physical, tangible device. The ratio of stimulated emission to spontaneous emission must be high. You can't just have a little bit of synchronization. You actually have to mathematically overpower the chaotic, random, spontaneous emission with the synchronized, stimulated emission. If you can force the vast majority of atoms to participate in the synchronized quantum dance, well, you've successfully built yourself a laser.
Which brings us to Section 5, the 4 pillars of laser light. Zooming back out to our everyday macro world, this microscopic synchronization gives the resulting beams some very distinct physical superpowers.
There are 4 critical features that define a true laser beam. These 4 pillars are exactly why this technology is so incredibly useful for humanity.
Let's walk through them quickly. First, because of that beautiful, perfectly timed stimulated emission we just learned about, the resulting light has a high degree of coherence. That means the light waves are perfectly aligned in both space and time. Second, it has higher directionality. It travels in a super tight, narrow path instead of scattering everywhere like a regular flashlight. Third, it has extraordinary monochromaticity. That's a big word, but it just means it is the purest single color or wavelength possible, just like my man's pure red 694.3 nanometer beam. And finally, high intensity. All that synchronized energy packed into a tight beam gives it the sheer physical power to literally cut through industrial steel, or on the flip side, perform the most delicate surgical incisions.
It's genuinely fascinating, isn't it? To realize that our modern world, from the fiber optics delivering this explainer directly to your screen to the scanners at your local supermarket, runs on these incredibly strict, microscopic quantum rules. We literally learned how to command individual atoms to sing in perfect harmony. Which really leaves us with a provocative thought. If we achieved all of this just by learning how to coordinate photons, how will our expanding ability to harness the microscopic behavior of a single atom continue to reshape our macroscopic world in the future? What other secrets of the quantum realm are just waiting for us to unlock? Thank you so much for joining me on this explainer. Keep wondering and keep exploring.